Good evening, ma'am.
Good evening. Can you hear me?
Hello.
Yeah, can you hear? Oh, sorry. Can you hear
I
me?
am not hear you. Yeah.
Okay. Just a minute, please. So I'm sharing my screen, and after that I will start. Okay. Can you see the screen? Hello. Am I audible? Hello.
Yes, you are
Okay.
audible,
Okay.
madam.
Okay. 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 I thought that you people can't hear me, so that's why. Okay, so in the last class, what we did about that quark model, and obviously in that quark model, we did about that octet and decoupled structure of quark models and quark particles, and all these things we have done. So just a continuation of that quark model, I am telling the last part of that previous lecture, because I think it will be very helpful for all of you in a little bit detail, so that it will be very good to understand. And after that we will move to the quantum chromodynamics, like color charge, color field, and all these things. Okay, so so let us start about the decouplet. I think in that previous class I was okay. Someone. Oh, okay. So decaplet, right? So in that decaplet, what we did in the last class, that q was there, and the expression was 3 cross 3 cross 3, which gives us um, just a minute, there is a problem. Which gives us 27. So that means 10 plus 8 plus 8 plus 1. Fine. So this type of configuration was there. So I am just talking about something like here, as in the previous class. In the previous class, what we did, here q and q was there. So like u, d, and s, there will be 27 combination, and in the previous class I have already talked about the 27 combination. Right now I don't want to talk these 27 combination anymore, but I want to say you something which is very important. Like see here, 10 particles, that 10 means that it will form a decaplet, right? So in that 10 particle decaplet system, there should be 10 particles, like in each and every corner there should be one particle, and as a whole 10 particle will be there. And just like the similar thing, here will be one octet, and another octet will be here also, and one singlet will be there, so that it will give a 27 combination. Fine. So like how many, like among the 27 combinations, uh, how much, I mean, what will be the 10 particles, what will be the 8 particles, and what will be the 8 particles, and what will be the last 6 one singlet anti-symmetric particle. I am talking about these things, like what will be the 10 particles, what will be the combination or configuration for that 10 particles. Okay, and what will be the configuration for one singlet here, and what will be the in between these particles configuration. See here, in the previous class what we did, I'm just talking something, that u was there in that 3 combinations, right? One was u, and another was d, and another was s. These 3 combination was there, but u and DDD and SSS, these three are basically fully symmetric, obviously, because you just if you interchange the place of these two or these two, then it will be same, like U, it will be very much similar. So that means it's a symmetric configuration, and the similar things for DDD as well as SSS. So these three combinations are totally fully symmetric. Fine. Now we want to say about some more, like these are the three particle configuration, and rest of the 7 configurations are what? Rest of the 7 configurations will be like that. UUD. So UUD means what? I can write UUD as like this. UUD plus UDU plus DUU. This type of configuration will be there for UDD configuration. Why? Because it's also follows the symmetric rule. Like symmetric rules is what? If I interchange U to D, that means if I replace all the U by D, then what? And also here U replaced by D, then what will be? UDU. Here U replaced by D, only one pair. Okay, so that means DUU and UD I am replacing, so that means what will be here? UDU. Just see UDU, DUU and UDU, yes, UDU and UDU, the same thing is coming. So that means this UUD is the symmetric configuration. Just similar of that UDD, USS, this type of configuration are totally fully symmetric. Now if I write UDS, this is also fully symmetric. How it is fully symmetric? Let's say if I write UDS as UDS plus USD plus DUS plus DSU plus SDU and SUD. Now if I interchange let's say here I am interchanging D in U as U and U as D. So what will be here? The particle will be SUD, which is same as this one. If I interchange this particle, then it will come as this one, like not particle configuration. So here also this will be same as this one, this will be same as this one. Yes. Hello?
Ma'am, fully symmetry are different things.
Just a minute. I think I am not hearing you. Yeah, can you please repeat again?
Ma'am, fully symmetry and symmetry, these are two different things.
Fully symmetry and symmetry.
Yes.
Yeah, like fully symmetry means, yeah, obviously fully symmetry and symmetry is a very same. Like there are 3 types of symmetry. One is the fully symmetric, and one is the fully antisymmetric, and another is the mixed symmetric. Okay, so fully symmetric means whatever I am talking right now, that UDD, USS and all these things, and UDS, these type of particles are fully symmetric. This type of configuration are fully symmetric, because if I interchange let's say U to D or D to S, it will become invariant. Okay, so it will be same. So this is a fully symmetric. Now I will talk about fully antisymmetric, and after that I will talk about mixed symmetric. Okay, so as a whole, do you understand? Like the fully symmetric means all the particles, like all the terms of that configuration will be invariant if I interchange U to D or D to A, something like that. Okay.
Okay, ma'am. That means if we change only one quark, then it also change all quark in the same time.
Yeah, like here if I write here UUD, so UUD we can write in terms of like this one, UUD plus, why 1 by root 3 I will talk about later. Okay, UDU plus DUU, I can write up like this. So here I have to search that this UUD configuration is fully symmetric or not. How can I see that? Here if I just interchange one pair of U and D, like one U will be replaced as D and one D will be replaced as U. If that type of symmetry is there, then I can say that this configuration UUD is fully symmetric. Let's say it is same or not. Like if I write here D instead of U and U instead of D, then here also let's say here D and then U, here U and then D. So what will be the final configuration? Final configuration after replacing these things, UDU plus DUU plus okay, no, it will be like this one, UDU UUD. UUD how? Here like I am changing this with this one, not this one. Okay, so this one and this one I am changing this pair. So UDU then DUD. So UUD will be there. So just see here, these three terms are the very similar of this term, the final term. That means it's an invariant under that symmetry, under that replacing of U to D and D to U. So that's why it is called fully symmetric. Okay.
Okay, ma'am. So can we write DDU?
DDU, yeah, fine. DDU. You are
We
talking
can
about
write DDU.
what? Hello?
In the previous example, we write U instead of D. That and
Sorry, I can't hear you.
I'm thinking, actually, ma'am, right? Hello, ma'am.
Yeah, hello.
Yeah. I am saying that if we write W and U instead of D, so it is DQ.
Sorry, Avram, I can't hear you properly. Like anyone can repeat what he is asking? Hello?
Here.
His signal is breaking.
Yeah, his signal is breaking. Like, can you understand what he is talking about?
No. His voice is continuously breaking.
Okay. I am writing a little more elaborately. Maybe it will be good for you. I can't hear you. Sorry, Avram. Like, let's say I am writing UDS. Okay. So if I write UDS like this type of configuration, I am writing at first and after that I will say that it is symmetric or anti-symmetric. Okay. So I am writing like that. Sorry. USD plus DUS plus DSU plus SDU plus SU.
Hello, ma'am. Now my voice is clear, ma'am.
Yes. Now your voice is clear. Yeah.
Oh, okay. I am saying that in the previous example we have UUD. Okay. So if we replace D instead of U, so it will become the DDU. So why we write only DUD,
No.
DUUD and the same things?
No, like UDD.
Yes. Yeah.
In we are replacing U to D and as well as D to U. It is not that only U to D. U to D as well as D to U. This type of expression I am using. So this type of expression means U can be replaced as D as well as D can be replaced as U. It is not that at the one time U is replaced by D. Simultaneously both are replaced.
Okay. So I think the same thing is happen.
Yeah. If same thing will come, if same thing will come, then we can say that it is invariant under this replacement, right? So this type of statement is for fully symmetric. I will talk about fully antisymmetric, then it will be very clear that it will how it can be a antisymmetric. Okay, so antisymmetric means you can say that
Yes, yes, ma'am.
let's say, okay, I will first say about it, symmetric, and after that antisymmetric. So this type, let's say UDS. Okay, UDS can be written like that. There are 6 terms. So it can be right like that. But right now what I am doing, I am just replacing U and D, whatever I am just taking about that, this type of expression I am using. That means U will be replaced by D, simultaneously D will be replaced by U. Fine. And the second condition is that D will be replaced as S. Okay, so that these two conditions I will apply in this expression. Then what will happen, if you just write each and every term carefully, then it will come as the same thing, because all the things are positive. I mean, in between these terms all the signs are positive. So if I just write here this one, or if I write this term here, that is not that much problematic, because all the terms are summation, right? So if I just interchange U to D or D to U as well as D to S or S to D, you can just also see this very similarly, that if I just change this type of configuration, then we can have UDS as the previous one. So that's why it is called as fully symmetric. So that means UDS configuration is also fully symmetric. Can you do that by your hand?
Oh, okay. Oh, yeah.
Like if you just interchange
Yes, yes,
U to
ma'am.
D, D to U, as well as D to S, S to D, then you can just see that
Yes.
UDS combination will be the same one which is written here. Okay.
Yes. Yes, ma'am.
Just write by your hand. If it is not the same, then you can just tell me. Okay. So
Okay, okay, ma'am.
yeah, that's why it is called as fully symmetric, right? So all the things
Yes, yes.
yeah.
Yes, yes. If we do this, my answer is same,
Yeah.
and that's called the fully symmetric.
Yeah, the answer is
But
same.
so the answer is same. Why do this? Why do spend more time in this to doing this
Yeah.
um,
Yes.
calculation?
Yes. See here.
This is the
Yeah. Okay. See here, all the elementary particle physics, in the all the elementary particle physics reading, and there are all the concept are totally based on some symmetry or some rules. Okay, so you have
yes.
UDS. In the previous class I was talking about 27 configurations, but among those 27 configurations, how many particles will be in decuplet state, how many will be in octet state, how many will be in second octet state, and how many will be that singlet state. We have to configure, we have to differentiate these particles, right? Otherwise how can we know that how many particles will form the decuplet, and how many particles will form the octet, and how many particles will form the singlet antisymmetric combination. So for doing these, we are just differentiating 27 configuration in such a way that first 10 particles will be fully symmetric, this one singlet will be fully antisymmetric, this 8 and 8 to octet will be mixed symmetric. Do you got my point?
Yeah, yes, ma'am.
So that's why I am talking about here very clearly, that how we can see that these all 10 configuration will be fully symmetric. And right now I will show you that this singlet will be fully antisymmetric. Okay, so now these 10 configurations, what was that? UUU, UDD, and that type of things, like DD, SS, this type of things will be there. I am not writing all the things. Then DDD and SSS and this type of things, and as well as UDS. These, there will be total 10 configuration in such a way that they are all fully symmetric. That's why they will form a decuplet. Fine?
Yes, ma'am.
Okay. Now, just a minute. Now I will talk about that one antisymmetric. How can we form that one antisymmetric configuration? Now let us write another UDS configuration, which is like that. UDS plus DUS plus SDU minus USD minus DSU minus SUD. Now do the same thing. That what was that? U interchange will be D and D will be replaced by S. Do the same thing in that configuration. Then what will happen? It will come out as minus of previous one. Do you understand? Like if you just interchange the same thing, that U will be D and D will be U simultaneously, as well as D will be S and S will be D simultaneously, then you can have minus of whole the previous one expression. Because here 3 terms are positive and 3 terms are negative. So if I interchange here, this term will be same as this term, but at that time minus is there. So that means as a whole there will be a minus in front of this expression. Do you got? Hello? Can you hear me?
Yes, madam.
I think you are doing these things, right?
Yes, of course.
See, I'm doing only the first one, UDS. Okay, so U will be replaced by D and D will be replaced by U, and what? D and S. So that means DUS. DUS is what? Like each and every term DUDS, like once at a time. Okay, I forgot to tell about that one. Once at a time, like UDS. Here D will be replaced by S and S will be replaced by D. That means this term will be there. But as there is a minus sign in the previous one, so that means as a whole there will be a minus sign in the final result. That means minus of this one. So what will be the answer? The answer will be minus of, let's say, UDS plus DUS, whatever it is there. So which is known as fully antisymmetric, and it will be once at a time. Like if you are doing in any expression U replaced by D and D replaced by U, in that next expression you can do this type of things. It is not that you are doing the same thing simultaneously. Obviously if D will replaced by U, then how can D replaced by S? Yes, so in one expression you can replace D to U, U to D, and D to S, S to D in the another term, so that you can have this type of expression with minus sign. So this is called the fully antisymmetric. And if you just write all the combinations among the 27, only one will be like that, which is fully antisymmetric. That's why we have one singlet state. And how that mixed state will come? Mixed state is little bit problematic. Like this type of things will be there. So if I just do the same thing, that UD DS, then one term will be, yeah, someone is talking. No, okay. So by that type of rule or by that type of configuration, we can made among that 27 states, we can made 10, 8 and 1, where all the 10 will be fully symmetric, this 1 will be fully antisymmetric, and this 8 and 8 will be mixed symmetric. Mixed symmetric means one term may be fully symmetric and another term may be fully antisymmetric, but it will be connected by positive or negative sign. That means it will be summation or it will be subtraction in between them, so that we can have a mixed symmetric. So I thought that it will be interesting for you, so that's why I was just talking these things. Now coming to the QCD, Quantum Chromodynamics. So in that QCD, why QCD is coming in the picture in elementary particle physics? Basically, we all know that quark is spin half particle, right? And if I write any baryon, then what is the configuration for baryon? Q, Q, Q. So if Q, Q, Q is there, then what will be there? Pauli exclusion principle says that no two similar spin will be in one state. Like if I write here half, 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 then it cannot be make a bound state. It should be a unbound state, or it should be a unstable state, because here all the three spin is in the same direction. Like if I write here U, 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 then it will be like that. So Pauli exclusion principle is not hold here, like it is not holding that a Pauli exclusion principle is right. But obviously in all particle physics we know that Pauli exclusion principle is the ultimate one. So we have to do something which can remove that type of discrepancy in our quark model, that in baryon QQQ configuration will be there, but at the same time there will be no Pauli exclusion principle violation. So this type of, like, it is a discrepancy that Pauli exclusion principle will be violated here. It's a problem. So to solve this problem, we will introduce one quantum charge, which is known that color charge. So color charge means what? Red, green and blue. So red means R, I am writing red as R, green as G and blue as B. So these are RGB, these three we are introducing in our quantum elementary particle physics reading. But like what it will do? It will do that, like if I am writing here for, let's say, delta plus plus, you know that quark content of delta plus plus is UUU. So if UUU is there, now if I just write spin of this also, then it will be like that. All the spin is half, like up. Okay. So all these three are the identical particle, identical UUU, identical quarks are there. So Pauli exclusion principle states that identical particle cannot have the same quantum state, but here we can see that delta plus plus have U up, U up, U up, which is the same quantum configuration. So that type of things is there. So but Pauli exclusion, if we don't want to violate Pauli exclusion principle, we have to do one thing, that okay, Pauli exclusion principle said that no two identical particle will be in the same state. We are making this and these are non-identical. How do we do that? Let's say U R, U G, U B, and we are talking about that UR and UG are not the same particle. So if these two particles are not same, then there will be no violation of Pauli exclusion principle. So that we can totally solve our problem that Pauli exclusion principle is not violated here also. That's why we are introducing here three colors RGB to resolve the problem of Pauli exclusion principle violation. Do you got my point?
Yes, ma'am. But I have a question.
Yeah.
What is red? Sorry, RGB. That means what is the physics of it?
Yes. Obviously.
What is the
Like,
physical property? It is a physical property. Otherwise, it is some definition. I
yeah,
think
it's just similar.
to reduce the Pauli exclusion principle.
Yeah, the main problem was Pauli exclusion principle violation. Okay, so to remove that Pauli exclusion principle violation, we have to include some another quantum charge, quantum number. So that's why we are introducing RGB, something like that. But why it is naming like that? Like R means red, but is it red in color? Is it green in color? The main answer of this question is that no, quark is not in red, quark is not in green in color, and it is not also in blue in color. Okay, but we are just assigning that type of name because each and every quark combination should be colorless. Colorless means if I write red plus green plus blue, means if you just like I think in the childhood you have painted something in your copy. So if you just color on that copy, then if you just mix one red, green and blue in the same proportion, then it will become as white color. Have you checked that? Like if I just put same proportion of red, same proportion of blue and same proportion of green, then and if I just mix up this, then it will become a white color. And white color means
Yes,
it's a
ma'am.
colorless, right? Like white color means there is no color. So like what is
But hello, ma'am.
yeah.
But my point is the baryon Rg and R rate. That means Rg and sorry. Okay. So here three baryon. Okay. And R, these are the fermions. Okay. And
Not baryons. You are the like
uh,
quark. U R U G U.
okay, quark. Okay. So the Rg and RR. Okay. So the red quark and the green quark. Both have the different physical properties or same physical properties.
Yeah, like UR and UG will be different. These two are not identical. If they will identical, then
Okay.
it will violate the Pauli exclusion principle, right?
Pauli exclusion.
Yeah.
Yes, ma'am.
So just differentiate these UU. We have to introduce some another quantum charge. But in your simple baryons and in your simple leptons, you did not heard about that color because in that situation there was no color, right? Like when we are just talking about proton or neutron as a whole, like proton means UUD. So as a whole, if I talk about proton, there is no mentioning that what is the color of proton. So to do that discrepancy, that in that quark level we are introducing three colors, but when we are mixing these three colors and when we are producing one particle, let's say proton, there should not be any color. That's why we are writing these type of quantum charges as red, green, blue, so that as a whole the particle will be colorless. Like it's a very analogy of any painting things. Colorless means we are not talking about these type of quantum charges in the particle configuration. When we are talking about proton, neutron, delta plus, sigma minus, sigma 0, there is nothing of this color. This type of color is only introduced when the problem was the Pauli exclusion principle. So to remove that Pauli exclusion principle violation, we are introducing this type of color. There is no but this color will be very problematic if I write this type of color as a color. Like if proton will be colored particle, then it will have a problem in that particle level configuration. Like if particle as a particle, if I talking about proton, as a particle if I talking about neutron, then there is no mentioning of color. You did not have heard about that color, that proton is red color, proton is green color. I think you did not heard about this because these all are colorless. Because all the things are colorless means white color is there. So to make this proton, neutron and delta plus plus and all these things colorless, we are introducing that type of configuration, that red, green and blue. Understand? Like it's a very natural and it's a very, what should I say, it's a very analogy with that painting thing. In that painting we are painted something which will give a red, green, blue in the similar similar proportion, then it will result as white color. So this type of configuration, this type of name is coming only for the colorless concept. As a whole, U for delta plus should be colorless. That's why we are writing red, green, blue like thing. Do you understand?
Yes, ma'am. Got
Yeah.
the point.
Yeah. Like so what is the main point or what is the caveat of that lecture is that each and every particle should be colorless. Like if I write here proton, so proton is what? UUD. So if I write like that, then I can write here, let's say UR UG DB. So these type of things should be there, because if this type of things will not be there, then the proton will be colored particle, but proton is not colored particle, and all the quantum, all the elementary particle physics study says that proton should not have any color. So to make a colorless particle, we are using RGB, that type of naming. Now I am just writing here one graph. I think you all have seen this type of graph. R.
Yes, Venn diagram. Venn diagram.
No. Which diagram?
Venn diagram.
Yes. So RGB, if I write this type of region, this region, you can see that this region is the intersection point of the all three portions. So this portion will give us white. So all the particles which will obey this type of configuration only will be applicable in our nature. Now I am writing here, let's say this portion, this. What is this portion? This portion is R plus B. There is no G. Then this type of portion I can write here R plus B, which should be G bar. Why G bar? Because G bar and G will make as a one, as a whole. So like I don't remember the color. If you just want, then I can write these colors also.
R plus B is black, ma'am. R plus B is black.
I totally forgot the color combination, but still, like if yes,
I do it.
Okay, you do. So whatever it is, it should be the antiparticle of G. Okay, the similar thing for here also. This portion says what? This portion says G plus B, which should be R bar, and this portion is what? This portion is R plus G, which should be B bar. Okay, so if I write here the delta plus plus configuration now, then what will be it? It will be R G B. Now if I just want to say any meson means, let's say Q bar configuration. So Q bar configuration if I write, then obviously it should be colorless. That means R bar, B bar, G bar, something like that will be there. Fine. Do you understand?
Yes, ma'am.
Okay, fine. Now we will talk about QCD, but before that I think you all heard about QED, that means quantum electrodynamics. So in that quantum electrodynamics, what was there? Basically nothing is there. In that quantum electrodynamics, this is a theory. So in that quantum electrodynamics theory, we are talking about electrically charged particle and how they are interacting. So let's say here E plus and E minus is there. I am talking about QED at first. So in that QED, E plus and E minus is there, and there is an interaction between E plus and E minus. So this type of interaction will be described by QED theory. And what is the mediator of this? Obviously the mediator is the photon, which is the chargeless and massless particle, and all the things are there. So just similar to that QED, we are talking about QCD. So QCD is what? QCD is the theory which can explain the interaction between two quarks. But obviously QED and QCD will be very different, because here in that QED you can see that E plus E minus may be there, or but here if I write here Q as a plus 2 by 3, here also Q as plus 2 by 3, still there is an interaction between them. But how can it possible that these two positive will attract? In strong interaction you can see that all the particles are very compacted, like inside that nucleus all the nucleons are very much compacted to each other, and they are attractive. The nuclear force is very much attractive in nature, but it can't be explained by electromagnetic force. We have to go beyond electromagnetic force to explain this strong interaction. So to explain the strong interaction, we are doing very similar of QED, but not exactly the QED. So what is in QCD? QCD is quantum chromodynamics. What is there? There we are just talking about Q, and Q is there, and in between this Q and Q one mediator will be there, which is charge mediator. In case of QED, gamma was, like photon was chargeless, but unlike of QED, in that QCD the mediator will be charged in the sense it is colored. Okay, so what is the mediator for QCD? I think you may all know, it is known as gluon. So gluon is colored particle, it should have some color. Okay, so if I write here one example, that let's just say I'm writing one example as, yes, this one, B and then here R. This type of diagram is nothing but the Feynman diagram, and this is gluon. So I already told that gluon is the colored particle. So colored particle means it should have some color. So color means, let's say it is like RG bar or RB bar, something like that. So if that type of configuration is there, that means as a whole it is not white color. So white color means there is no color. So this type of things are colored particles configuration. In that expression, like here in that Feynman diagram, what I am doing, B will convert to R. Sorry, this is a typo. B will convert to R. Then what will be the configuration for gluon? The configuration will be like RB bar. Why? Because if I write B plus, like B and RB bar, then as a whole it will be R. So that means B will interact with R through the gluon RB bar. So G will be colored. Now you can ask me that what type of color will be there in G, like what is the color, what is the quantum charge for gluon. So the quantum charge for gluon is a matrix form, it is not a single color. Why? Because we have three color R, G, B. So from that three colors we can make it we can make so many configurations, right? So if I write here some of the configurations like R B bar, R G bar, B R bar, B G bar, G R bar, G B bar. These six combinations are totally colored combination. Like R B bar is also color, R G bar is also color. There is nothing which is colorless. Now let's say one more configuration which is this type of things. R R bar plus G G bar plus B B bar by root 3. Is it colored or not, colorless? Can you please tell? Hello.
I think it is colorless, ma'am.
Yeah, it is colorless. So it will be a quark like a gluon configuration or not. Like as I already told you that gluon should be colored. So that means this type of configuration is not possible for gluon. Okay.
Yes, ma'am.
So only these six configuration will be possible, and another combination will also be possible. I am writing here this type of combination. B bar. No, sorry. So just a minute here. 1 by root 6 R bar plus B bar minus 2 G bar. Why it is not colorless? Because if you see here each and every term R bar, B bar, G bar, this type of things will give you colorless particle. But as a whole, if I just interchange R to B, B to R or B to G, G to B, then it will give us a anti-symmetric configuration which is not a colorless particle. Like if the symmetric configuration is there in that previous one case, this case R, if I interchange R to G, G to R or R to G to B, B to G, then it is a fully symmetric configuration. Fully symmetric configuration will give us a colorless configuration, but in that configuration it is not a fully symmetric, it is a anti-symmetric configuration. If I interchange this type of R to B, B to R, B to G, G to B, then it is obviously a colored state, and obviously it may be a state for gluon also. So what I did all the 6 configuration, as well as this one is 7th configuration, and the 8th configuration is like that, R bar minus B bar. Now you can see, you can ask me that why R bar, B bar is there, why not G bar? Obviously G bar will be there, like all the combination of like that, like R bar minus G bar or B bar minus G bar, something that there may be so many configurations. So this type of configuration will all have a colored state, and they will all can describe as a gluon. So these things are there for the gluon colored configuration. Okay, so now if I write just a minute. Okay, now I am writing here some very simple thing, that what is the experimental evidence for color. In the previous class I was talking about experimental evidence for quark. Now we are talking about what is the experimental evidence for color. Like why we are talking about color. Obviously why we are talking about color, I have already explained that to remove the Pauli exclusion violation. But what is the experimental evidence of that? Okay, so if I write here E plus E minus to hadron, E plus E minus to hadron. E plus E minus was leptons, and if these E plus and E minus will collide each other, head-on collision will be there, and if there is so much energy of E plus E minus, then it will form so many hadrons, what is right now going in LHC. So in that type of configuration, in that type of expression, if I calculate the cross section of this process, this type of cross section, E plus E minus goes to hadron, this cross section in experiment and theory, this theory is 3. If I don't want to include color in our theory, if I want to include color in our theory, in our quark model, then the result is very near to 1. So what I am talking about, like if I calculate that type of interactions cross section, then the experimental value as well as theoretical value will be similar only when we will take color in our theory. So this is a experimental evidence for color. Now one more experimental evidence was there, that neutrino magnetic moment. We can only know about neutrino as well as not neutrino, neutron proton magnetic moment when we will introduce our color theory in our quark model. So this type of things is there. Now as a summary, what should I tell? As a summary, U, D, S, T, C, B, these 6 quarks are there. Each and every quark can have 3 color R, G, B. So that means what will be the total combination? 6 particle can have 3 each. So that means 18 types can be there, as well as U bar, D bar, S bar, T bar, C bar, B bar. All the 6 antiparticles should be there, and these antiparticles should have each and every one 3 colors. So that means again 18 types as a whole. 18 plus 18, 36 type of quark can be found in nature. So when we are drawing that elementary particle physics classification, we will talk about 2 fundamental particle, one is quark and another is lepton. But in that quark there will be 36 combination, and in that lepton there will be 12 combination. How 12 combination will be there? Because electron, mu, tau, 6 combination will be there: E bar, mu bar, tau bar. And if you will consider neutrino, then this type of things: nu E bar, nu mu bar, nu tau bar. So as a whole, this 12 type of combination will be there for lepton, and for quark 36 type of combination will be there. So like when we will talking about classification of elementary particle physics, then we can see that there in any elementary particle physics book you can see that there is 36 types of quark as well as 12 type of lepton. So how 36 is coming? 36 is coming due to that flavor as well as color charge in our quark model. So if I write only flavor, then there will be only 6, 6, 12 will be there. But if I write a color in with that flavor, then there will be 36 combination. Okay, so this type of things is there. And I think in quantum chromodynamics there is not that much more. If you have any question about quantum chromodynamics, you can ask, or otherwise in the next class we will talk about that direct and compound nuclear reactions questions, because someone asked me to do that. So that type of things were there in the quantum chromodynamics. And obviously there are so many things in quantum chromodynamics, but as a very simple notation, as a very simple footing, I am talking all the things. So yeah.
Ma'am, the word is chromo. It comes from the color sense.
Yes,
The word
obviously.
quantum chromodynamics,
Chromo is due to
just
the
like the
color change.
electrodynamics.
Yes. The mediator, which is gluon, it is itself a colored particle. So color is totally all over the quantum chromodynamics. But unlike that in that QED the mediator is not colored, sorry, not charged. Okay, but still it is quantum electrodynamics. So why quantum electrodynamics? Because we are talking about charged particle there. Here also we are talking about colored particle. So that's why quantum chromodynamics is naming. And one more thing is there, like unlike that QED, in that QCD, gluons are also interacting each other. But photons are not interacting each other because they are chargeless particle. But here in that gluon case, gluons as they are colored, so they can also interact each other, which will make a very complicated situation. Obviously that's why still now we don't have that much knowledge about proton, neutron, inside that nucleus what is happening. We are not that much aware of this because it's a very complicated theory. Okay, like just unlike of QED, in that QED photon is not interacting each other, but here gluon is interacting with each other.
Yes, ma'am.
So but still we are talking about
Also
this.
the
Yes.
yes. The in quantum chromodynamics, we have charge particle also.
Charge particle is colored particle, like charge in the
Uh,
sense that
uh,
they have color.
that is, we don't say they have a charge. We
Charge
say
means,
only the color.
see, charge means we can say charge in any sense, like uh, E plus, E minus, that type of charge we are talking all the time. But RGB, these type of things also known as charge. But charge in which sense? Colored charge. So if I talking about quick hypercharge, quick charge, so this all the things are charged. Like if strangeness is there, it is also a quantum number, which can also be known as charge, but it is not that electric charge. Electric charge means E plus, E minus, this type of things says that okay, plus means positive charge, electric charge, minus means positive, my negative electric charge. But if I want to talk about colored charge, that means RGB or the colored charge.
Okay, ma'am. That means the both charge have different properties.
Yeah.
Uh, like just like the two charge with the just like the if we say the Coulomb's law, the same the two charge is a repulsion and the unlike charge is retraction. So here that charge is not in the sense of a color charge.
Yes, like uh, that is the main thing here. Like in that weak charge as well as in that electromagnetic charge means electromagnetic interaction says that two positive charge repulse each other and two negative charge repulse each other, but one plus one minus will attract each other. That is the electric charge, that is not a color charge or anything else. But when we are talking about proton, neutron and all this, so inside that nucleus there are all the nucleons which is very compactly interacted. So if I talking about quantum electrodynamics inside that nucleus, then it will not be applicable for there, because inside that nucleus proton all the protons are compacted in a very strong, with a very strong force. But it cannot be said that it is, this force is electromagnetic force, because electromagnetic force says that if two proton is there, then proton two proton means positive charge, obviously it should be repulse each other. So that type of things cannot be described by quantum electrodynamics. That's why we are talking about something more which is known as quantum chromodynamics. In that quantum chromodynamics, what we are talking that okay, inside that proton one quark level is there, inside that quark level color charge is there, this color and another color will interact each other through gluon so that they will form a compact form. And that's why, I mean, that's how nucleon will be stable, all the nucleons will be stable inside that nucleus.
Okay, ma'am. So we can say that the Coulomb's law is not applicable for color charge.
Yeah,
Also,
obviously,
we can
like
say that.
it's not a
Uh,
electric charge, that's why it is not applicable here also. Like Coulomb charge is only applicable for electric charge, just like that Newtonian charge,
yes.
Newtonian law is applicable for that massive particles. So the similar things is there here. Non-abelian gauge theory will be there, so which is totally different from that Coulomb charge as well as that Newtonian gravity, you can say these things. So it's totally different from all these things. It's a very new and it's a very unique thing which says that two proton can also interact each other very strongly, which can form a compact nucleus. Okay.
So the one request, ma'am, it is possible to some problem on this quantum chromodynamics in the next week.
Okay, so
Actually we can ignore the compound problem because someone is me. I was told that the problem will be discussion on the compound nucleus, but I have changed my mind. So I need some
okay.
problem discussion on the because net problem. Sorry, net examination has complete. So
How was your exam?
we uh, good, but not very good.
Okay. So, like for from that nuclear and particle physics, how many questions were there?
That means conservation law. Because some conservation law I have done.
Okay, like whatever it was there, you have already solved all the questions, right?
Yes, yes, yes.
Okay, then it's fine. So you want some problems about that quantum chromodynamics or that quark model, basically.
Yes, 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 ma'am.
Okay, we'll do in next class. Okay,
Okay, ma'am.
yeah,
Bye.
bye bye. তা কি করবে, কতক্ষণ চালাবে, কতক্ষণ ভাট বকবে? না না, আরেকটা বাচ্চা ডক্টর মোহাম্মদ বলে একটা, সে পিএইচডি করে কমপ্লিট, তাও এই সব ক্লাস করে।
চর্চা